Okay, so the random sampling error will have that variation component will be sigma, if we know sigma, which is the variation of that opinion in the population, the real population parameter, and the sample size component will be the size of the sample. But the relationship between the sample size and the random sampling error is not linear, and you're gonna use a square root in order to estimate it. Okay, so imagine that I have a sample of 100 people. So the square root of 100 people is 10. Okay, and imagine that the actual variation of the opinion about immigrants is 17.2. So what I'm going to have is a random sampling error of 1.72. Okay. So what? What does it mean? How do I interpret that result? That might be your question, of course. That's a logical question. How do we interpret that result? Okay. So here is where I use this idea, or here's where assumptions play a role. Remember that assumptions are critical for scientific inquiry, right? So we have this assumption here in inferential statistics. We say, okay, if we know the true variation component in the population, which is sigma, then we can use the central limit theorem and the properties of a normal distribution to estimate mu. Okay? Implicitly, we also have another assumption, but we're gonna see it very soon. And the assumption is that that distribution is normally distributed. Okay, let's talk about it. Let's start by the central limit theorem. What is the central limit theorem? The central limit theorem is this idea, is a statistical theory that tells us that as we draw samples and infinitely, or we have samples larger as an infinite number, positive number, of course, these samples or this sample would be normally distributed. Okay, that doesn't tell us anything, right? But what is a normal distribution? A normal distribution is a specific or a particular kind or a special kind of distribution that is perfectly symmetrical and unimodal. So you need to remember those things that we learned in I think this was the third class, about what is a perfectly symmetrical and unimodal kind of shape of a distribution. But basically, this normal distribution has a specific characteristic, and is that it has in the range of more or less one standard deviation, the 68% of all observations. So look at here. In this area, we have most of the observations of that sample of whatever is that variable. Okay, remember, let's think about again this idea of the thermometer about immigrants in this imaginary state. So whatever is this value, most people are concentrated here. The opinion of most people in that state in the sample are concentrated here. Okay, and 95% of all observations will be in a range of 2 standard deviations from the mean. Okay, and basically all the observations, almost 100% of observations, will be in the range of more or less 3 standard deviations. Okay, this is a graph that I actually created in R, based on, very similar to this, to what we have about this thermometer, feeling thermometer about immigrants. Remember that the mean we said was 57, I guess. The value of mu was 57, and we have this variation from 40 to 70. So to some extent, if this is normally distributed, we have the mean here, and we have most of the values in a range between 50 and 65, something like that, and very few values are outside those boundaries. Okay, but here is important to introduce a new idea, and it's the idea of the C-scores or C values, and the idea of standardization. Standardization is when you, in order to apply the properties of a normal distribution, you standardize the values of a sample. right? And you standardize those values because you want to know how each value is located in relation to the standard deviations and the mean. Okay, so you standardize their effect. How do you standardize that effect? So you have here a formula. You create these things called C values. So the C value is equal to the deviation from the mean divided by the standard unit, which in this case is the standard deviation. Okay, this seems kind of difficult right now, but it's going to make sense. This is the mathematical formula. X is a particular score, X bar is the mean of that sample, and sigma is supposed to be the standard deviation of the population parameter. Okay? Okay, so let's see this example. We have here, I want to show you how to estimate the C scores or the C values. And basically what you have here is that is a mock example of a sample of 100 members or 100 individuals, I'm sorry. And you have the mean of this sample is 3 and the standard deviation of the population is 1.41, right? So if you have, for instance, a value of 7, so the deviation from the mean is going to be 4. So it's going to be 4, right? And the C value is going to be 2.83. If you have a value of 3, for example, there's not going to be deviation from the mean, and the C value is going to be 0. And if you have a value of 0, the deviation from the mean will be minus 3, and the C value is going to be minus 2. Okay, so what does it mean? It's not intuitive, right? But let's use the normal distribution to try to interpret this. And actually the C scores are created or are used to talk or to locate any specific score in a normally or in a normal distribution context. Okay? So remember that we said that the mean is 3 in this sample. When we standardize this distribution of this sample, so the mean is going to be 0. Okay? And the whole distribution of this variable for this sample will be in these small values of C. So we're going to have 68% of the data in more or less one standard deviation, or I'm sorry, one C value. Almost 95% of all the observations will be in more or less 2 C values, and very few cases will be in the range of more or less 3 C values. Okay, so let's interpret these results according to this normal distribution. For instance, if we have a value of 3, there's no deviation, and the C value for that reason is 0, right? If you have a value of 2, the deviation is going to be minus 1, and the C value will be minus 0.7. So this score will be located just one standard deviation below the mean. So it's going to be close to the mean, right? And finally, if we have a value of 0, the deviation will be minus 3, and the C score will be minus 2.1. So it's going to be in this area of the whole distribution. Okay? But what does it mean, these things? These tell us things about the probability that these events occur. Okay? So 0 will be a very unlikely event because it happens just, I don't know, it's not even in the second standard deviation or C value of this distribution. And please remember that this normal distribution not only tell us things about the x-axis, the y-axis has the frequency of that distribution. For that reason, the mean is the event that most happen because it's the most frequent. And in that case, 0, which is located here, is an event that is very unlikely to happen. So The c-values are very powerful because they allow, and the standardization is very powerful because that allows us to make probabilistic inferences about where or the occurrence of these events. Not only where are they located in relation with the mean and with the standard deviation of this sample, but also to what extent we can expect that this happen again if we solve this distribution of this sample. So probabilistic inferences is when you want to say the likelihood of the occurrence of an event or a set of events, right? According to the distribution of that sample and the information that you have available for you, okay? And something that is important to keep in mind is that the most likely outcome is the one that most frequently occurs. So remember that what is this table of normal distribution? In the x-axis, what you have here is the values of C. In this case, is the value of C score. And remember that the values are standardized here. So the mean now is 0. And each value, like a moving from 0 to 1, is like a moving from the mean to 1 standard deviation, 2 standard deviations, 3 standard deviations, right? But in the y-axis, even if we don't have it here, is the frequency of the occurrence of those events. So whatever is in the mean is in the mean because it is the most frequent event, right? Similar to this idea of the mode, remember that the mode is the value that is repeated more times in the sample. So it's similar to the mean. So the mean is here because it's the most frequent kind of event, right? And because it's here is the most likely kind of event. So if I ask you something like imagine that we have, again, so let's see this table again. If the mu, or if the mean of this sample is 3, so we know that 3 is the value that is most likely to occur because it's here. Again, and think in terms of 0, for instance. If 0 is below the mean of the C-score, this standardization, and is like at 2 points of C-value below the mean, which is here. So what can we say about this kind of value is very unlikely to occur according to this sample. I hope this makes sense, but it's very important that you learn and you understand this basic concept, okay? So again, the most likely outcome is the one that most frequently occurs. We don't have enough time to cover all the rules of probability and all the ideas of probability, and we probably will need a whole class, and even there are whole courses or semesters to study probability theory. But just to give you a glimpse of what is probability and this idea of that I just told you about, the importance of this relationship between the frequency and the likelihood of an event, okay? That's so powerful that there is even a theorem in statistics called the maximum likelihood theory that helps you to predict what is or to estimate what is the most likely event based on this idea of the frequency. But let's think about this. So if we have a coin, what is the probability of getting a head when tossing that coin? It's 0.5, right? It's the same probability to getting a tail, right? For that reason, tossing a coin is one of the most simple random sampling mechanisms or random mechanisms because the odds are equal. So it's just is the one of the trials or one of the tools that are more fair, right? And what is the most likely number to be rolled on a dice, for instance? So none of them, because all of these numbers have equal probability to be rolled, which in this case is 1 divided by 6, 1 out of 6, or 0.16, right? But what would happen if we have a dice with the number 3 repeated twice? In that case, 3 is going to be the most likely outcome because there is a higher probability that 3 is going to appear more frequently than the other numbers, okay? So that's very basic, but that's the most that's the most important idea that you need to have in mind right now about probability. If there are more things you can learn over time, but this is simple but important. Okay. Okay, so we know now many things. We know about the standardization. We know about that the standardization and the normal distribution and the central limit theorem help us to make predictions about, or to make probabilistic inferences or predictions about the occurrence of an event, right? So just to recapitulate. So we know, okay, so we know that the random sampling error in this case is 1.7. Again, what does it mean for us? Okay, how do we interpret that result? Because it is impossible to know the real value of mu, so we don't know this value of the population parameter. So we provide a range of values that we are confident that like the mu is within those boundaries, okay? That range of values is called confidence intervals. So, and I like this idea, and the term is beautiful because this is the interval in which we feel comfortable to say that the mu of that population falls, right? You can say is from this upper boundary to this lower boundary, okay? And the most common standard is 95% confidence intervals. And that 95%, I don't know if you remember that I gave you some proportions and the idea of normal distribution, right? And that matches with this idea of 95% confidence intervals. Actually, this is based on the idea of normal distribution. So let me see if I have here. So let's return to this idea of normal distribution, right? So I said that 95% of all observations in this sample fall in this range of more or less 2 standard deviations, right? So my confidence interval is this area, because what happened outside that area is very unlikely. And for instance, far beyond 4 standard deviations even doesn't occur. It needs to be a very extreme kind of case to happen, a very outlier case. But most cases will be here. So I feel comfortable to say that mu, the parameter of the population, will be around these boundaries. Okay, that's what 95% confidence intervals tell us. Okay, so we provide, as I said, the upper confidence boundary and the lower confidence boundary. And how do we do it? We use this formula. So we have the mean of the sample, and we sum, in this case, 1.96, I'm sorry, which is, or could be 2, but in this case, 1.96 is the value of C that is like the 95% of the observations in a normal distribution are actually within more or less 1.96 C values, okay? But we use the shortcut of 2 because it's very close to that 1.96, and it's easier to estimate it with just 2, okay? But it's the same. So we have the estimated mean, in this case was, I don't know, whatever, but could be 55.2 in the example of the billionaire. And we sum 1.96 and we multiply 1.96 for the random sampling error, or the standard error, which in this case we said was 1.72. And in this case, the upper boundary will be 58, and in the case of the lower boundary will be 51. So what all this tells us? So if the billionaire asks us, okay, so what did you estimate will be the mean feeling thermometer of the electorate in this state about immigrants? So you can say confidently that according to this sample of 100 people, that mu, or that mean feeling thermometer, will be in the range of 51 to 58 points. Okay,